Okay, these properties we're talking about, they only hold for relations. So these special relations we're talking about, special properties, are for relations on cross products of a set with itself. So it doesn't matter what S is, it just has to be crossed with itself, because I can't even talk about reflexive if I'm talking about letters, comma, numbers, right? I couldn't ever have AA if I have only things like letters in the first element and numbers in the second. So I have to come from the same set to have something like reflexive. So here's some formal definitions. A relation is reflexive if, for all x in S, here we go with predicate calculus, XX is in R. So I'm going to say, you know, R has a property if reflexive if, for all x in S, XX is in R. So R is in S cross S if XX is in R for every single element of S. So the relationship we were just talking about, divides, that is reflexive because 2 divides itself, 3 divides itself, 5 does, 6 does. All the numbers divide themselves. So that's a reflexive relationship. What's something that isn't reflexive? Greater than, right? 2 is not greater than 2. So that's not reflexive. It's actually irreflexive. So there's actually 3 things we can have. We can have a relationship that's reflexive. It might not be reflexive, or it can be irreflexive. So it's irreflexive if none of the reflexive points are in there. So greater than is an example of an irreflexive relation, because you can't ever have an element being greater than itself. But there's lots of things that are neither reflexive nor irreflexive. So I'll give you some examples later, but I just want to point out that there's lots that are neither. So these are not the only 2 choices, because these are not opposites, right? If I negate this for all statement, I don't get this for all statement, right? I get a there exists statement. So these are not opposites. These are not exact opposites. That's what I wanted to point out. If they were exact opposites, then we would have just one of, you'd always either be reflexive or irreflexive, but that's not the case. Okay, so let's go on to some other definitions. Most of these are things that you really understand already. We just don't normally talk about them in predicate calculus. So we understand symmetric really well. Everybody understands that well. Okay, so for all x and y in S, if xy is in R, then what is in R? Yx is in R. So that's the definition for symmetric. If I have a point in there, I can flip-flop it and still be in the set, in the relation. So less than or equal to is definitely not symmetric, right?
Correct.
So asymmetric is kind of like the opposite, but it's really, again, it's sort of like irreflexive and reflexive. It's not really opposites. It's sort of extremes. Like reflexive is the extreme that we have all of the points, and irreflexive is we have none of them. Symmetric is we have all of the opposites, and asymmetric is we have none of the opposites. So for all x, y, and S, if xy is in R, then that implies that yx better not be in there. Absolutely not allowed. And that's why we can't have 2, 2 in there. So an asymmetric, that's one definition. The other definition is that it's antisymmetric, and we'll give you a definition of that in a second. So a relationship is asymmetric if it's both antisymmetric and irreflexive. So we're going to do antisymmetric in just a second. There's lots of ways to write this definition. But for any two numbers in S or elements of S, if they're not equal and one relates to the other, I can't reverse the order. Another way to write this is, let's see. So this is just another way to write it, so you can use whichever definition you like.
Move up a little bit.
Yeah. So for antisymmetric, another definition, so these are two equivalent definitions. If xy is in R and yx is in R, then that means what? This says if
x is not equal to y.
it actually means that x needs to be equal to y. This one right here says if x is not equal to y and xy is in R, then yx can't be in R. The only way that these both could be in R then is if x and y are equal. So antisymmetric, the way I remember antisymmetric, it's just like less than or equal to. So I can't reverse the order unless I had the same thing in both sides to begin with. So if x is less than or equal to y, I can't change x and y unless x equals y. You know, if 3 is less than or equal to 5, I can't reverse the order. 5 is not less than or equal to 3. 3 is less than or equal to 3, and I can change the order because 3 is still less than or equal to 3. So this looks like a complicated definition, but you all understand it because it's just like nothing's symmetric except I'm allowed to have some reflexive points in there. And then the last thing we need to define is transitive. So how would you write transitive?
X, Y, Z.
If x, y is in R and
Y, Z in R.
y, z is in R, then what?
X, Z. I mean, yeah.
That's right. X, z is in R. So transitive, we've been doing that all semester. P implies Q, Q implies S, then P implies S. So we should be pretty used to transitive by now. We haven't called it that, but it's the same thing. That's why hypothetical syllogism comes first on your list. Right? Questions?
Just hold on 1 minute.
So we're going to do a couple of more here, some examples. And when you want to check for these properties in a relation, you need to check for the definition. So usually I'm going to give you some words that describe what the relation is, and then you're going to put them into these definitions and see if they work. Okay, so we're going to do some examples like that just now.
By actually plugging in numbers, or?
No, we're going to plug in the definition of the relation.
Okay.
So normally I give you a definition of a relation like this. X, y is in R is logically equivalent to x is less than or equal to y. And then I can put, for x, y is in R, I can put x less than or equal to y. Right?
Mm-hmm.
So if I wanted to check and see if this relationship is transitive, I would put x less than or equal to y and what?
Y less than or equal to z.
Y less than or equal to z and x less than or equal to z, and then see if this implication is true for all x, y, and z. If it is, then it would be transitive. So we're going to do some definitions like that, and we're going to test out these. So that's what you're going to do every time you get a relation and you want to see what properties it has. Then you're going to plug it into the definitions and check them. So they're these are predicate statements, and you'll be able to check whether they're true or not.